Students, today we are going to see CPU scheduling algorithms and deadlock in operating system. So, this in CPU scheduling algorithms we are going to see how it schedules the algorithms and how multiple process scheduling is happening and real time scheduling is happening, and also some algorithms used by the CPU for scheduling. Main thing is CPU is based on utilization is based on IO burst and also CPU burst. So, IO burst is whenever the process is executing, whenever the process is asking for input output devices, it is called as IO burst, and whenever the process needs some calculation, that means processing needs to be done, then it is CPU burst. So, in this example diagram we are going to see, we are seeing that both CPU burst and IO burst are interchanged. When CPU burst is executing and whenever the process needs some IO devices, it will wait for the IO, then it is called as IO burst. Again the CPU burst will continue and then IO burst. So, similarly it gets both the things are happened one by one. And the next thing we are going to see is CPU scheduling. For CPU scheduling, the OS needs to check whether the process in which state. So, for that it is using the states of process, whether the process is in switching from running state to waiting state, or whether the process needs running to ready state, or whether it is in waiting to ready state, or it is getting terminated. It depends on it checks all the states of the process, and depending on the states it is going to allocate the algorithm, and the algorithm is based on non-preemptive method and also preemptive method. Preemptive method is nothing but even the process is executing with the resources, whenever the next process comes based on the priority, if that process needs to be executed, the process which is having the resources will be taken from the process and give it to the second process. That is called as preemptive. Voluntarily we are releasing the resources from the first process which is executed and giving the same resources to the next process. And non-preemptive is until the process gets finished, even though the next process has the highest priority, the resources will not be grabbed from the process and it will not be given to the second process. So, the first process will be allowed to complete its execution. And the dispatcher is the main reason for identifying the process and dispatching the process to the CPU for execution based on the algorithm. So, while any process is being switched for any algorithm or CPU execution, it needs to do all these things, that is switching the context. Switching the context is whatever state it may be, it needs to be switched to the some other state, that is switching context, and switching to user mode. For processing it needs some input from the user, so the OS needs to switch to the user mode. For every process it needs all these things to make it ready, and jumping to the proper location to restart the program for depending on the state which is stored already. And dispatch latency. Dispatch latency is nothing but the time taken for the dispatcher to stop one process and start the another process. So, when one process is executing, when another process arrives for execution, the first process will be stopped and the second process gets started. So, the in between time is called as dispatch latency. And scheduling criteria. So, what is the condition? Criteria is nothing but the condition which needs to be checked for scheduling the process. So, the main conditions we have to see is CPU utilization, whether if this process is being scheduled, whether it uses the CPU properly or not. So, it needs to be checked by the operating system before it is allocated to the processing. Then throughput. Throughput is how much output it can give. If this process is allocated for the CPU for execution, whether this process gives maximum output or minimum output. And turnaround time. So, turnaround time is nothing but amount of time for executing the process from the starting to the end. The time taken by the CPU for executing that process is called as turnaround time. And what is waiting time? Amount of time a process is being waiting in the ready queue. So, as we all know, only from the ready queue the process will be taken and given to the CPU for execution. So, that means that the OS will place all the process in the ready queue only for the first time. So, the waiting time by the process before it gets scheduled is called as waiting time. And what is response time? So response time is amount of time taken whenever the process is submitted to the CPU, and the time taken by the process to get started and till it produces the first response, not the complete output. The time does not depend on the complete output given by the CPU. Instead, the time taken by the CPU for starting that process and giving the first response to the user, that time is called as response time. And main thing is the CPU cannot take all the process and execute it as such. So it needs to check so many criteria, and that criteria should satisfy all these conditions. So the condition is maximum CPU utilization. If a process is being taken for execution, the CPU needs to check whether it gives maximum CPU utilization and maximum throughput. That means the output should be very specific, and it should be very clear. So maximum throughput and minimum turnaround time. So what is the turnaround time? The time taken for execution is called as turnaround time. That turnaround time should not be maximum. If a process takes maximum turnaround time, only on that day the CPU can execute only that process, all other process will be in the waiting state. So the OS needs to avoid that. So for that it will check the minimum turnaround time of the process, and it will take only the process which is having minimum waiting time and minimum response time. And so many algorithms are used by the OS for executing or getting executed the process. So the first algorithm which we are going to see is, these algorithms are very, very important. The OS will select whichever is having the average waiting turnaround time very less. The OS is going to select that particular algorithm and allocate that to the process. So the first algorithm is first come first served scheduling. So whichever process comes first, that will be scheduled first. That is the meaning of it. First come first served scheduling, or FCFS scheduling. So we have given some examples, like we have three process P1, P2, P3, and the burst time is 24, 3 and 3. For process P1 it is 24, for process P2 it is 3, and for process P3 it is also 3. So we have to draw a Gantt chart in order to identify the average waiting turnaround time. Right. So the Gantt chart starts from 0th. According to the diagram, the Gantt chart starts from 0th milliseconds. According to this algorithm, it is first come first served. So whichever process came first, that needs to be allocated. Process P1 is the first process which came, so we are allocating the process P1. So it starts from 0, and the burst time of that process is 24. So at the 24th millisecond, the process P1 is being completed. So from 0 to 24 milliseconds, process P1 is going to execute, and after that the second process which came is P2, and its burst time is 3. So from the 24th milliseconds, it will take the 3 milliseconds and completes its execution. P2 will complete its execution. So totally it completes its execution by 27th millisecond. And similarly, we have to take the third process, that is P3. Its burst time is also 3. So from 27 plus 3, so at the time of 30th millisecond, P3 gets executed. So totally it took 30 milliseconds for executing these three processes, and we have to calculate the waiting time and average waiting time. So for calculating waiting time, we have to check process P1, how many milliseconds it has been waited before its execution. So process P1 didn't wait, so it started from 0th milliseconds itself. That's why the waiting time for P1 is 0, and for P2 it waited, the P2 waits until P1 gets completed, so it waited till 24 milliseconds. So 0 for P2 it is 24, and P3 waits till 27th milliseconds for P2 gets executed. So P3's waiting time is 27. So you have to find the average waiting time. 0 plus 24 plus 27 divided by number of process, we have 3. So you get 17 milliseconds. So if you give these three processes in the same order which came into the CPU will complete it within 17 milliseconds. So the OS needs to check other algorithms also in order to allocate it to that allocate the process, because whichever algorithm gives the lowest milliseconds, that algorithm will be chosen by the operating system. So this is our first algorithm. According to this, it took 17 milliseconds for getting executed all the three processes. And the same set of process which came in different orders, first P2 and then P3 and then P1 came. So automatically the Gantt chart gets changed. So the final again it also took 30 milliseconds to complete, but anyway the waiting time of the process gets decreased. For P2 has started at the 0th millisecond, so P2 is 0. P1 it waits for 6 milliseconds, so P1 is 6. P3 it waits for 3 milliseconds to get executed, so P3 is 3. So you add all the three, 603 and the total process we have 3, so you will get 3 millisecond. So depending on, according, if the OS is using FCF as scheduling algorithm, depending on the order of arrival of process, the waiting time gets decreased. And what is a convoy effect? Convoy effect is, suppose if the first come first served doesn't have any conditions, criteria to allocate, therefore shortest process will be waiting for the longest process to get completed. So that type of waiting needs to be avoided. So that effect is called as convoy effect. If the shortest process is waiting for the longest process to get completed, that means it will wait for more number of times. It doesn't know the actual time it gets executed. That effect is called as convoy effect. And the next algorithm CPU uses is shortest job first scheduling, SJF scheduling. Shortest job first is whichever job is having the burst time very less, that job will be taken, and this SJF will be either preemptive way or non-preemptive way. What is preemptive way? Whenever a process is executing in it line and another process came with the shortest burst time, means the process which is in execution will be relieved and this process will be executed. So we voluntarily take out the process which is executing. So that is called as preemptive. And non-preemptive method is, even though shortest burst time comes as the next process, when one process is executing, we will not relieve the first process, we will wait until it gets completed. That's why it is non-preemptive scheduling. So it could be SJF, could be either non-preemptive and also preemptive method. So we will see one example for that. We have 4 processes, P1, P2, P3 and P4, and for that everything we have arrival time and also burst time. Arrival time is 0.0 for P1, burst time is 7, P2 2.0 and 4, P3 4.0 and 1 and P4 5.0 and 4. So we are going to allocate it according to non-preemptive method now. So it starts from 0th milliseconds, whichever is having the burst time very less, that needs to be allocated first. So we are allocating P1. So P1 only it came now at the 0th millisecond, only we have P1. So P1 is allocated, but its burst time is 7. But at the when it is P1 gets executed, at the time of second millisecond P2 arrives. That means as this is non-preemptive, we are going to allow the process P1 to execute completely, then only we are going to allocate the process P2. So after P1 gets completed at the 7th millisecond, what is we are going to allocate the second process now. So if you see here, P2 arrived by 2 milliseconds and P3 arrived by 4 milliseconds. That means before P1 gets completed at the 7th milliseconds, we have 2 processes, P2 and P3. So we have to check the shortest burst time. If you check for P2 it is 4, for P3 it is 1. So 1 is lesser. So we are going to allocate P3 even though we have P2 because of this algorithmic type. So we are allocating P3. So P3 is burst time is only 1. So it gets completed by 8th millisecond, and afterwards we have P2. At the time of 5th millisecond, P4 also arrived. So we have to compare the burst time of both P4 and P2. If you compare, P4 is also 4, P2 is also 4. So we can take whichever came first. So we are taking P2. So P2 is allocated. Its burst time is 4. It completes its execution by 8 plus 4, 12 at the 12th millisecond. And if you take the only process which is left is P4. So we are taking its burst time is 4 again. So 12 plus 4 at the 16th millisecond, P4 also gets completed. So the average, we have to calculate the average waiting time. So if you see P1 doesn't wait for any process to complete, so it came by 0th millisecond. So P1's average waiting time is 0. P2's average waiting time is 8, and P3's average waiting time is P2's average waiting time is actually 8, but P2 has arrived only at the time of 2nd millisecond. So it doesn't wait that 0th millisecond and 1st millisecond, it didn't wait. So that's why we are subtracting the 2 milliseconds from the waiting time of P2. So therefore 8 minus 2, the waiting time of P2 is going to be 6. And the waiting time of P3 is, it waited till 7, but still it arrives only by 4th millisecond. So 7 minus 4, 3 milliseconds, it has been completely waited. So we are taking 3, and for P4 it waited till 12 millisecond according to Gantt chart, but it arrives only by the 5th millisecond. So it didn't wait for the previous 4 milliseconds. So we should not take that. So we are subtracting that 5th millisecond. So 12 minus 5 is 7. So totally you add it and we have 4 process divided by 4, so you will get the average waiting time as 4 milliseconds. So this is of non-preemptive method. And the next example is of preemptive SJF. So as I have told you, what is a preemptive method? Even though the process which is executing, if any process comes with the shortest burst time, the execution process will be taken out. So we will see that. So again we are taking the same process, 4 process, its arrival time is given and also its burst time is given. According to preemptive SJF, we are at the time of 0 only P1 has arrived, so we are taking P1 as the first process. So it starts from 0, and when it is executing at the second millisecond, P2 has arrived. So what is the arrival time of P2? It is second millisecond. So at the time of second millisecond, P1 is executing now, P2 has arrived. Okay, so we have to check when it is executing, as because of preemptive method, so we have to check the shortest burst time for either whether P1 is having the shortest burst time or P2 is having. So P1 still needs to execute 5 burst time is there. For P2 it is only 4. So we just shortest P2, obviously P2 is shorter. So we have to voluntarily move back the process P1 and P2 needs to be allocated. So that's why P2 has been allocated at the second millisecond. And similarly P3 has arrived by 4th milliseconds before P2 gets completed, because P2 is having 4 burst time, but at the 4th millisecond only it has completed 2 burst time. Still it has, P2 is having 2 burst time, P3 has arrived. So again the OS needs to check for the shortest burst time. So P3 is having 1 and P2 is having 2. So obviously which is shortest? P3 is shortest. That's why P2 has been removed and P3 is allocated. So P3 works for 1. So it starts from 4 and ends with 5th millisecond. So after that P4 also at the 5th millisecond it came, but the burst time of P4 is 4, but for P2 it is going to be only 2. That's why P2 has been allocated first. So from the 5th millisecond, for 2 milliseconds P2 will complete its execution. So totally 4 milliseconds of P2 is over. So and after that P4 is there. P4 is having 4 milliseconds. Obviously if you check for the P1 is still waiting because it is having the 5 milliseconds. It is the maximum millisecond it has, that's why it is waiting still. But obviously now we have only 2 process, so we have to check with the 2 process. P4 is 4 and P1 is 7. So which is the shortest one? P4 is shortest one. So we are allocating P4. So it is executing for 4 milliseconds. So it completes by 11th millisecond, and after that only one process is left, that is P1. It executes for 5 milliseconds. So it completes by 16th millisecond. So we have to calculate the average waiting time. So we will calculate. So the process P1, it didn't wait for any thing. So we cannot say it 0 because process P1 gets completed only by 16th millisecond. So it waited for some time. So we have to check that value. So you check that value. Process P1 waited for 11 milliseconds. But it is not the actual waiting time. Why? Because already P1 has completed its execution for 2 milliseconds. So you subtract this 11 minus 2, it is going to be 9. So that is the waiting time of the process P1. And you take P2. P2 has also executed 2 times. So the first 2 is not the actual waiting time. So we take the waiting time as 5, but actually it has completed 2 already. So that's why 5 minus 2, it is going to be 3, but actually P2 came only by 2 millisecond. So that's why we are subtracting 3 minus 2, the waiting time is actually only 1. Okay, and you take the P3 process. So if you take the P3 process, it is only one time it is being executed. That's why it has been executed. So the value is, the waiting time is going to be 4. You take the 4 and you check when it has arrived only by 4th millisecond. So it doesn't have any waiting time. At the time it arrived, it has been allocated. That's why the waiting time of P3 is going to be 0 only. 4 minus 4, 0. And you take P4. P4 waiting time, it has been executed only one time. So you take the P4 waiting time as 7, but it arrived only by 5th millisecond. So 7 minus 5, only 2 milliseconds it has been waited. So for P4 it is 2. You add all the 4 waiting times and divided by 4, you will get 3 milliseconds. So if you are using preemptive scheduling, it is taking only 3 milliseconds, but if you are using non-preemptive scheduling, it is taking 4 milliseconds. So whichever is lowest, shortest, or whichever waiting time is lowest, the OS will allocate that process order to the in that algorithm only. And the next type of algorithm is priority scheduling. So priority scheduling, it could also be a preemptive one and non-preemptive one. As the name itself, priority scheduling, every process will be given a priority, and depending on that priority, the allocation will be there. If a process is having highest priority, that will be allocated, and then lowest priority is going to be allocated next. And priority number is an integer value, any number you can give, it is associated with each and every process comes to the CPU for execution. And in this priority scheduling, you have a problem such as starvation. So starvation, nothing but all the higher priority process will be executing always, and the lowest priority process will not be executed until the highest priority process completes. So that is called as starvation. Its waiting time is more, the lowest priority process waiting time is more. And the solution for that is you add aging. So what is aging? When we will say aging, whenever our year gets increased, we will say it as age. Similarly, if any process is having the lowest priority, and if you think it is waiting for a long time, then you have to age it, you have to add the value of it, so that it will come to the highest priority level, and it could be executed. So that is called as aging. As time progresses, you increase the priority of the process. And the next type of scheduling is round robin scheduling. So round robin scheduling is, as the name itself, it is the round robin. So all the process will be given equal chance of executing. So for that, it will use a time quantum. So depending on the time quantum, the process gets executed. So for all the process, they are giving the equal time quantum. Say for example, if you are giving quantum equal to 12, so we are having 4 process, and each having its burst time, its own burst time. If you draw the Gantt chart for that, you have to take for each process 20 milliseconds only. So the first process P1 gets started, and it gets finished by 20 milliseconds, and it cannot be continued even though it has the burst time 53. So it still needs to execute 33 milliseconds, it will not be continued. Again the next P2 process will be taken, and it gets finished because it's having only 17 milliseconds. We have given the time quantum as 20, therefore P2 gets finished, and P3 will be taken next, and then P4 will be taken next. Afterwards, the P1 will be again given the same chance. That's why it is a round robin scheduling. After P1 gets completed, P2 will be given. After that, P3, again P4, again it will start from P1. So until the process gets its burst time gets completed, it will be given a chance, depending on the time quantum 20. So that is actually round robin scheduling. Even though the time it gets completed is 162 milliseconds, even though the time is very large, but it has a better response than SJF. So because each process will be given equal chance, so there won't be any starvation, you don't need to give any aging for any process. So it's a better way. And the next one is multi-level queue scheduling. So multi-level queue scheduling is, we are going to, again it's equivalent to priority only. So we are going to select process, and depending on the process type, we are going to allocate levels for that. So lower level and also again higher level processes. So lower level process, so what is the advantage of using this multi-level is, lower level process can use some type of scheduling, and higher level process can use some type of scheduling. It is not that each and every one is correlated. Right, and it could be a fixed priority scheduling also. That means we can give a time quantum for each lowest process and also highest process. For both of them, we can even use the same scheduling like round robin, give the same time quantum, so automatically there won't be any starvation. Each and every process will be executed with the equal rights. So that is the advantage of multi-level queue scheduling, and this is the diagrammatic representation of multi-level queue scheduling. System process is there. Interactive process is nothing but the user is going to give some input, and user is going to take the output. That processes are called interactive process, like railway reservation, airline reservation, everything comes under, all online things comes under interactive process. And interactive editing process, suppose you have a chance to edit the values in the process, then it comes under interactive editing process. Batch process is group of similar process will be grouped together. Those processes are called as batch processes. And student process, so very lowest level has been given for the student process. It is not this is the only queue you have to maintain. Depending on the process which you get, you can change the level of the queue, and you can give also highest priority and lowest priority for that queue depending on your process, right. And the only disadvantage of multi-level queue scheduling is, whichever process we have kept in the highest priority, it will be there only, it cannot be moved to any lowest priority, or lowest priority process cannot be moved into highest priority. There won't be any movement between the levels of queues. But in multi-level feedback queue scheduling, it is overridden. That means a process can move between the various queues. Even whichever process is getting starvation in the lowest priority, that can be moved to the highest priority depending on the time. So multi-level feedback queue scheduling, it needs to check certain conditions for moving that process. It could be number of queues, how many number of queues it is maintaining, and what is the algorithm it is using for each queue, and which method can be used to upgrade the process. Upgrading the process is moving the process from lowest to highest or highest to lowest, and methods used to determine when to demote a process, when to make the process to go to the lowest level. It is everyone knows process is in lowest priority and it has been moved to highest priority, means we will be happy. But if our process is in highest priority and it is being moved to lowest priority, means we cannot be happy. So likewise, the methods, it needs to check whether this process can be demote to a lowest priority process or not. It needs to justify that, then only it can demote it. And methods used to determine which queue a process needs to enter, whether it needs to be a highest priority queue or the lowest priority queue, or in between queues, in which queue the process needs to be executed. So that also decided by the operating system whenever it moves the process from one queue to another queue. And this is the diagrammatic representation of multi-level feedback queues. So each and every queue can use anything, any type of algorithms. The lowest is using FCFS and the highest is using quantum 16, that means round robin scheduling it is using. Quantum is 16 milliseconds, some process is going to execute at quantum 8 milliseconds. So any process can be moved from quantum 8 milliseconds to quantum 16 or to FCFS. So the movement is possible with the multi-level feedback queues. And the next one is multiple processor scheduling. So what is multiple processor is, more than one processor is going to be used for executing the process. So the CPU scheduling is more complex when we are using multiple processors. So for each, if it is using a single processor, it needs to check more conditions for making the process to execute in that single CPU. But if it is having more processors, then it needs to give more constraints for the process to enter into that multiple CPUs. So for that, it is using a homogeneous processes is there, asymmetric multiprocessing is happening. So what is homogeneous is, homogeneous processor will use only same type of process, will execute only the same type of process. Those process can be given in homogeneous process. It will also be included inside the multiprocess. And what does asymmetric multiprocessing is, only one process can access the system resources for its execution. That is asymmetric multiprocessing. But the advantage of using this multiple processor is the load could be shared. That means the process can be shared or divided into modules to each and every processor, and it gets executed very quickly. So that is the advantage of using multiple processor for scheduling. And it could be a real-time scheduling also. So real-time, it means either hard real-time or soft real-time. What is hard real-time? It needs to be executed only at the particular or a stipulated period of time. So the time limit is there, critical timing will be there. Within that timing, it needs to complete its execution. So that is hard real-time system. So that type of process will be given to the hard real-time systems, and whichever process doesn't need any timing, so that process will be given to the soft real-time systems. And I have told you about dispatch latency. A diagrammatic representation of dispatch latency is here. The event is there and the response to event is at the end. In between, so many processes are being happening, interrupt is there and some conflicts is there whenever it starts its execution, and after that, after the conflict has been resolved, it will be dispatched and the real-time process gets started and finally the response has been given. But what is a dispatch latency is? The time it taken for starting its execution and for the first output which is being given, that is real-time process execution starting stage. So that is called as dispatch latency. And that's all with CPU scheduling algorithms, and we are moving to the next topic, deadlock. So deadlock is nothing but you are moving in a traffic, and both the sides you are having you are moving in a road, and both the sides you have some car jammed. So which car needs to be moved first? So you will get a problem obviously. So that problem can be resolved only when one side of car gets gives space for other. So this situation when all the cars has been jammed in a road is called as a deadlock. So how come it can be related to OS? So we will see. So we are executing all the process, right? So at the same time, if any process, more than one process is getting executed now at the same time, when one process is having a resource which is asked by the another process, and the second process is also having some resources which is needed by the first process, that means no process gets completed at a time. So I will give you with an example. Process A is executing with the magnetic tape and process B is executing with a printer, but process A needs printer for completing its execution and process B needs magnetic tape for completing its execution. So none of the process gets completed now. It will be waiting for process 2 to release, process 2 will be waiting for process 1 to release. So this situation is called as a deadlock. So in we are facing the same situation in traffic, but any one of the side of people, if they relieve or if they give some space, the other opposite side traffic will be cleared, so that these people can also move. But as this is system, so we have to make the system to release something. We have to make the system to release the resources for gets the process completing. So it's a important and also very crucial thing. Critically it is maintained by the operating system. Without this deadlock, if the deadlock is not maintained by the operating system, then no process will be executed completely, right. So a set of block process, each holding a resource and waiting to acquire the resource of another process in the set, then it is called as a deadlock situation. So I have given this example. So in a deadlock, resources types are called as R1, R2, and any number of resources it could be there, it could be RM resources. The resources are nothing but memory spaces, CPU cycles and everything, IO devices comes under resources. And each resources has being hereafter, it has been referred as R for resource and W for instance. So what is meant by instance? A copy of that resource is called as a instance. Suppose I have two printers, I am having two instances of resource. So this instance is referred with W, and each process whenever it starts its execution, it has to do these things. It needs to request a resource, then only OS will allocate it. If it needs some printer, the process needs to request it to the OS, then only OS will allocate the printer to that processor. After requesting, it will be allocated, the process needs to use it, and after using that resource, it needs to release that resource. So these things needs to be properly followed by the process. If the process is following these three things properly, there won't be any deadlock. But if any one of the process, if it is not following this properly, definitely the system will lead to a deadlock. So if deadlock happens, the operating system cannot be able to, if the deadlock cannot be corrected by the operating system also, the operating system cannot be able to continue its process. So what are the characteristics of deadlock? When we can say a process has come to a deadlock situation? So for that we are having four things. One is mutual exclusion. Mutual exclusion is when only one process at a time can use a resource. If there is a condition like the resource can be used by only one process at a time, then it is called as mutual exclusion. The other process cannot ask that resource for execution. Hold and wait. So the hold and wait is whenever a process is holding a resource and waiting for another resource. So definitely it will lead to a deadlock. And no preemption. So no preemption is nothing but we cannot be able to voluntarily release the resources from the process. If a situation is like that, a process will have its resource and wait for another resource till the OS gets closed or till the execution gets completed. But the deadlock comes for OS, so it is not going to close the execution, so it will be in the deadlock state. So circular wait. Circular wait is nothing but you take three processes. I will tell you with three process example: P1, P2, P3. If P1 is waiting for the resources held by P2, and P2 is waiting for the resources held by P3, and P3 is again waiting for the resource held by P1. So that means P1 will not release, P2 will not release, P3 will not release until it gets its resources. If there is a circular wait, then we can say, if there is a cycle, then we can say it definitely it leads to a deadlock. So these four situations, one is mutual exclusion. Mutual exclusion is nothing but only one process at a time can activate the resource or access the resource, the other process will be waiting until it gets completed. So the one point is mutual exclusion, or hold and wait is there. One process is having a resource and it is waiting for another resource to get completed, that is hold and wait. And no preemption is voluntarily we are not going to grab the resources from the process, then it is no preemption situation. And circular wait is all the process is waiting circularly for other process having its resource, then it is circular wait. If these four conditions arises, definitely we can say that it will lead to a deadlock. And for that the OS is going to use a method called resource allocation graph. With this graph the OS can identify whichever process is in deadlock state. So all the in that graph all the vertices will be V and the edges is going to be E. Okay, what is V? V is nothing but the vertices are nothing but resources and process. They are given as vertices. How many processes you can have? Any number of processes from P1 to Pn, any number of processes can be in the system. And R is nothing but resource, I have told you. Any number of resources it could be there. R1, R2 up to Rm, M number of resources could be there. And two edges will be there. One is request edge, another one is assignment edge. What is a request edge? Whenever a process P1 is asking a resource, is requesting a resource means if Pi is requesting a resource Rj, what is I? Set of processes is given in I and set of resources will be given in J. So if a process Pi is requesting a resource Rj, then that edge is called as request edge. What is an assignment edge? When a resource Rj is allocated for the process Pi, then it is called as assignment edge. So we will see the graph, and before that process will be given in circle and resources will be given in square, and inside that square you will have small squares. All those squares are called as instances. Instances are nothing but copies of resources, and Pi request instance of Rj means a circle will be requesting a square. And Pi is holding an instance of Rj means Rj, a circle, is holding a square. Okay, right. So these are the diagrammatic representation of resource allocation graph for deadlock. So see this example. In this example, process P1 is requesting R1. R1 is having single instance of R1. So P1 is requesting R1. That single instance of R1 is allocated to P2. Okay, the single instance of R1 is allocated to P2. Again, the P2 is requesting a resource of R3 and that single instance of R3 is allocated to P3. And similarly, you have R2 resource which is having two instances. One instance is allocated to P1, another instance is allocated to P2. R4 resource is there, but it is not asked by any of the process. So see here, this is the resource allocation graphical representation of resource allocation. And this is used by the operating system before any resource is allocated to the process. And how can the OS will identify whether any deadlock has happened in the process and resources which is being there with the resource allocation graph. So this example diagram will tell you this. See, P1 is requesting R1 instance and it is having R2 instance. P1 the process, it is having one instance of R2 and it is requesting an instance from R1. But P2 is requesting P2 is having a instance of R1 with it, and it also R2 instance is also with P2, and it is requesting a resource instance of R3. Okay. So what I am saying is, if P1 needs to get completed, what is needed for P1? An instance from R2. Okay. Then only P1 gets completed. Whereas R2's instance, R2's one instance is with P2. So when P2 will complete, P2 is having R1 instance and R2 instance, but it is still requesting for R3. Where is R3? R3 is with P3. So P3 is being allocated with R3 and P3 is also requesting R2. So only when P3 gets executed, it will release R3. Only when R3 is released, P2 gets completed and it will release R2 and R1. Only P2 when releases R2 and R1, P1 can get completed. So anyway, P3 cannot complete its execution, P2 will not complete its execution without P3 completing it, and P1 also cannot complete its execution. So this is called as a deadlock. So you can find a cycle over here. So P1 is requesting R1, again P2, R3, P3, and P3 is requesting R2, R2 is held by P1. So a cycle structure is available with this graph. That's why this graph is having a deadlock. OS will conclude that it is having a deadlock. Then it will analyze what solution can be given for this deadlock. Suppose if any one of the process releases one resource, automatically everything will be gets finished. We will see this. See, if R2 is being released by P1 means the R2's one instance which is requested by P3, it will get it, and it is also having R3's resource. So with that two resources it will complete and release R3 and R2. So the R3 will be available for P2 for its execution. So it is having R1 and R2's one instance. With R1, R2, R3, P2 gets completed. So automatically it releases all R1 and R2 which is requested by P1. P1 is having one instance R2, it is requesting R1 only. So P2 will release the R1 after its execution. So P1 gets R1 and also R2, it will also complete its execution. So the only way is any one of the process resources needs to be grabbed out so that that process gets stopped and other process can complete its execution. So here resource allocation graph with a cycle. So basically if a resource allocation graph has some cycle, there is a possibility of deadlock, but it doesn't mean that definitely it needs to have a deadlock. So we will see this with this example diagram. So see here P4 is allocated with one instance of resource R2, but it is not requesting any resource. So once P4 gets completed, it will release the instance of R2 which is requested by P3. So the P3 will grab the R2 instance and it is having one instance of R1. So it gets completed and it releases R1 and R2, and R1 instance is needed by P1. So P1 will get it, P1 gets completed, and P2 doesn't ask any instances of resources. It is already having an instance from R1. So with that R1, P2 gets completed, so P1 also gets completed. So totally all the process gets completed. Even though you find a cycle here, P1 is requesting R1, again P3, R2 and P1. You find a cycle here, but even though you have a cycle, it won't come to a deadlock. So that the thing is, if any cycle is available in resource allocation graph, there is a possibility of getting a deadlock, not all times. Right. If graph contains a cycle, so when it comes to a deadlock, if only one instance per resource type, a resource is having only one instance, if that instance is allocated to one process and another process is requesting it, definitely there will be a deadlock. But if that resource itself it has more instances, so the more instances can be allocated by allocated to any number of processes which is asking, therefore there won't be any deadlock. And if several instances per resource type, possibility of deadlock. Even though it has several instances, if all the instances are allocated to all the process but still some more process is requesting it, means definitely it will get a deadlock. So if a graph contains no cycles, there won't be no deadlock, definitely we say that. But if it contains a cycle, there is a possibility of getting deadlock. And methods for handling deadlocks. So deadlock has happened now. What to do? So we have to ensure that the system will never enter a deadlock. Whenever the process is asking for a resource, we have to check if the resource is allocated to the process, whether it leads to a deadlock or not. So then only we have to allocate it. So we have to ensure that the system will never enter a deadlock. Okay, and allow the system to or else allow the system to enter a deadlock and then recover. So we have so many recovering techniques. You can apply the techniques and we can recover it very easily. But not all the cases, in some cases. So you allow the system to enter a deadlock state and then you recover it. Or else you ignore the problem and you say that the system will never enter into a deadlock, definitely. That means you can allocate whatever resources you want to all the process. So these are the methods for handling deadlock. One is either you ensure that the system will never enter a deadlock. So you are going to choose only the process like that for allocation, or else you make the system to allow to deadlocks because you have so many resources. Oh, I have so many techniques. So definitely I can make the system to come out of the deadlock. If you have that confidence, you allow the system to enter into a deadlock and then you can correct the deadlock. Or else you ignore the problem. So whatever is there, at least for 1 hour it is running means okay, it is for me, 1 hour is okay for me. I will allow it to, whether it gets deadlock or not, I will allow it to work. So that kind of mentality is there for you. Then you allow the system to execute, ignoring all the problems which it has. So these are the methods for handling deadlocks. So an OS creator, a OS programmer needs to compare all the methods for handling deadlocks, and he needs to study completely about the system. Then only he can allocate the algorithms or whatever he wants for the process to execute in the CPU. So this is the main work of the OS programmer, right? And deadlock prevention. So the first one we have seen is once deadlock has happened, how to avoid it. And the second one is how to prevent the system from entering into the deadlock. See, I have so many processes to execute now, I have some resources, I want to ensure the system should not enter into the deadlock. So I want to prevent it. So for that, what I have to use? I have to check all the 4 conditions. What are the 4 conditions? Whether it doesn't have the mutual exclusion, whether the system is not having hold and wait process, or whether it doesn't have the circular wait process, whether it should not have any no preemption techniques. So all the 4 techniques needs to be checked in order to avoid or in order to prevent the system from enter into the deadlock. So what is mutual exclusion? So if you are having a shareable resources, then mutual exclusion is not there, it is sharing. That means mutual exclusion is not there. So whenever non-shareable resources for the system is there, definitely you can say that the system will go into a deadlock. So that time we have to be very careful, or if you are having non-shareable resources, it is not allocate the process, more than one process to a CPU, right? And hold and wait must guarantee that whenever process requests a resource, it does not hold any resources. What is hold and wait? A process is having a resource and it is waiting for another process to release its resource. So that is called as hold and wait. So before entering into the system, you have to ensure that there is no hold and wait there. If any process is having the resource, once it executes, it needs to release the resources. So that should be ensured. And the process will be allocated to the resources will be allocated to the process only when the process is not having any of the resource with it. Otherwise, it will not be allocated any resources. You have a condition, you give the condition for OS, so that OS will not allocate it. So definitely you won't get a deadlock. And the next one is no preemption. What is a no preemption? If a process is holding some resources and it is it requires next set of resources which is holded by another process, means you give some time, you don't allocate it immediately. Okay, and also the preempted resources cannot be given to each and every process as such. Instead, it should be in a queue, and depending on the need of that resource, it needs to be allocated, and process will be restarted again to continue its execution. It will not be continued, it does not continue at the place where it has been stopped. So once the resource has been allocated only, it needs to be restarted. Before that, the process has to wait until it gets the resources. And circular wait. So there will not be any preemption. We are not going to grab any process resources and give it to another process. Instead, we are waiting for one process to release its resource. Once the process, the resource is released, it will be maintained in a queue, and in the queue only it is going to be from the queue only it is going to be allocated to other process depending on the need, and the process is again restarted after it gets its resources. And circular wait. What is circular wait? So you have to what is a circular wait is, if all the process is waiting for other process to give its resource. So to avoid that, you get at the first time itself how much resources needed by the process. Okay, so if that resources can be allocated, if that resources are free only, you can allocate the process to the CPU, otherwise you cannot allocate it. So you get the total ordering of resources needed by the process in the beginning itself, so that you can avoid the circular wait. And deadlock avoidance. So how will you avoid a deadlock? So it requires some additional information. What I have told you, every process needs to know how many resources it needs to complete its execution. So that information needs to be given prior to the OS before it gets started. And the deadlock avoidance algorithm can be used to check every time, even though the process is allocated, every time a deadlock detection algorithm is applied by the OS to check whether it has entered into a deadlock. If any of the situation it entered into the deadlock, means it will stop its execution, it grabs its resources and give it to another process. and it will not allocate that process any resources and it will stop its execution. So, for that it is using deadlock avoidance algorithm. That means we are allocating resources to the process, making it to execute whatever it is needed, whatever it has asked, and making it to execute. So, after that execution, only after it gets completed, then the resources are going to be at that time deadlock detection algorithm is applied by the OS to check whether at that particular time the process has entered into the deadlock state. So, the resource allocation state is defined by what is the state? Number of available and allocated resources depending on the demand of the process, maximum demand of the process. So, resource allocation state is nothing but number of available resources in the system and number of allocated resources. For example, if a the process needs 50 resources and the system is having only 20 resources, definitely that process cannot be taken into account. So, that is the main concept for avoiding the deadlock. And every time OS checks whether the set of process which is executing is in a safe state. Safe state is nothing but it is not in a deadlock state. That means any of the process is not waiting for any other resource. So, that state is called as safe state. So, resources if P1 resource needs are not immediately available, P1 has to wait until P2 completes its execution and give it back its resources. So, then again before allocating, the OS will check whether the process will be in safe state when it is allocated. Right. The basics factors, if a system is in safe state, the OS will think that there won't be any deadlock, and if it is in unsafe state, definitely it may lead to a deadlock. And for avoiding, we have to ensure the system which is allocated with the resources, process which is executing is allocated with the resource will not enter into a deadlock state. So, that we need to ensure, then only the process will be the process will be in a safe state. And this is the diagrammatic representation. If a process is executing in a safe state, at any time when it goes for an unsafe state, it will lead to a deadlock. And what is resource allocation graph? So, you have one more edge is being added. You have two edges already, request edge and assignment edge. You are adding one more edge, claim edge. That means if a process is requesting a resource, then you have to put an edge that it has been requesting with a dotted lines. So, the dotted line is nothing but claim edge. So, we will see this in the diagram. That is P1 process is allocated with the resource R1, but it is asking for the next resource R2. So, it is claiming. That is why we have given a dotted line. Similarly, P2 is requesting R1 resource, and also it is claiming one more resource, that is R2. So, that is why we have given it in a dotted lines. And unsafe state. So, how will you say with this dotted line it is an unsafe state? An example for that, P1 is allocated with resource R1 and it is asking for R2. Similarly, P2 is requesting R1 and it is allocated with R2. That means P2 is having R2 resource and also it needs R1 resource. R1 resource is held by P1. So, who is going to give this process P2? R1 resource, P1 will not give because it is also requesting resource R2. So, again it is not going to give. So, therefore, P2 will not be completed and also P1 will not be completed. So, definitely we can say that if P1 is asking for R2 means this state, this process, this resources will definitely lead to a deadlock state. So, it should not be allocated. So, the OS will know that, and for that it is using an algorithm called Banker's algorithm. So, Banker's algorithm is mainly used when a resource is having multiple instances, definitely it will come to a deadlock. So, it uses this Banker's algorithm to check, and it needs a prior information about the resources. The process needs to give the prior information about the resources, and whenever a process is requesting a resource, it cannot be allocated immediately. So, it needs to wait, and after the process gets some resources, after its completion, definitely it needs to release it. A particular, even if it is not completing at a particular period of time, it needs to release the resource, right. And you have some variables we are going to use with this Banker's algorithm: available, max, allocation and need. So, it has been given that if available of j equal to k, k is nothing but it is meant for instances of resources. Available of j equal to k, the meaning is the k instances is available in a resource Rj. The meaning is k instances is available in a resource Rj. J meant for resource, I meant for process, already we have seen it. And what is max of I comma j equal to k? That means k instances is the maximum resource needed by the process Pi. K instances of Rj resource is maximum needed by the process Pi. And what is allocation of I comma j equal to k? K instances of resource Rj is allocated to process Pi. I is meant for process, j is meant for resource, and k is meant for the instances of resources. And need of I comma j equal to k, what is that? K instances of resource Rj is needed by the process Pi. So these are the data structures which we are going to use it in Banker's algorithm. So this is the Banker's safety algorithm. Why it is called a safety algorithm? We are going to check the safe state of the process system or system which is allocated with the process, right. So we are having two variables, work and finish. Work equal to available number of resources is allocated to the work. Suppose the system is having 50 resources that is allocated to work, and finish of phi. Finish is the variable which is going to have state true, false or true. Finish of phi is false whenever the system has not completed its execution. Finish of phi becomes true whenever the system gets completed its execution. A system is nothing but number of process, some number of resources has been allocated. So that is called as a system, right. So in the second step, it checks whether finish of phi is false and need is less than work. What is need? The resources needed by the process, and what is work? Available resources. So available resources is 50 for example, and the process needs 80. Can we allocate the system? Can we allocate the system with the process? No, we cannot allocate because we are having only 50 resources. How can I allocate for the 80 resources needed process? So what I will do is, I will not allocate that. So instead, if it is less than, suppose the system is asking only 20, I am having 50 totally, but it is asking need is only 20, so I can allocate. So it will check this condition for all the process in the system. If any one of the process is not satisfying this condition, it will not allocate. It will ensure that the system will enter into the deadlock because it is an unsafe state. So it will not make the system to execute. And if suppose everything is okay for all the process, the need is less than work and the finish is not there, finish is only false, it is not true, that means it has not been completed, then you are allocating the resources to the process. After allocation resources to the process, for all the process, you set all the process finished state to true. That means all the process gets completed with the available resources, and this will be continued for all the process, and at the end it will check whether for all the process the state will be true. If it is true, the system is in safe state, then only it will allocate. So this algorithm is nothing but the safety algorithm. The OS will check for each and every process which is going to be allocated to the resource, whichever system is going to be executed now. So for those process, it will check the resources need and the availability of the resources in the system, then only it will allocate the system to, or it will allocate the resources to the process and allow the system to execute. Okay. So this is the safety algorithm. And resource request algorithm. So whenever a process wants a resource to execute, it needs to request it to the OS. So for that it is using a resource request algorithm. So OS will check this algorithm whether it leads to any deadlock state, then only it will allocate it to the process, otherwise it will not allocate. So for that, if request is less than need, so what is request? The process is requesting some resources, it is less than need. See, some process it needs only 50 resources, but it is asking for 100 resources. So what it will do with the remaining 50 resources? It will keep it with it. So what happens? Other process will be waiting for a long time, so obviously it will lead to a deadlock. So we should not allocate that. So it is checking the first condition itself, whether the request is less than the need of the process. Then only, because it is going to claim its resources in the beginning itself. So every process resource need will be known by the OS already. So it will check whether the request is less than the need, then only it will go for the next step. And it also checks whether the requested resources is available in the system in the second step. If it is available, then it is going to allocate it, and the allocation gets decreased, and the need will also be decreased for the resources. So that means available equal to available minus request. So available is 50. What is requested now? Suppose 20 is requested, means available now becomes 30. And what is allocation? Allocation equal to allocation plus request. Allocation is 20 I am going to allocate. What is actually requested is 50. So again it is going to be allocated resources 20, and the requested allocation already is 0. Now I am requested is 20, so 0 plus 20, the allocation is now 20. And what is need? The need of the system is totally 50, but now it has been allocated with the request 20. So the remaining resources needed by the process is going to be 50 minus 20, 30. So it will do all these calculations and check if it is safe, the resources are allocated to particular process P, or if it is an unsafe state, the resources will not be allocated. So these 3 steps will be checked again and again. If any of one step is not there, it will not allocate the any of one step is not okay, then it will not allocate the resources. So this is called as resource request algorithm for each and every process. And what is deadlock detection? How a deadlock can be detected? You have to allow the system to enter into the deadlock state, and then only you have to detect the algorithm, use the algorithm for detecting. Once it is detected, if you have deadlock, means you have to recover it. So these are the steps the OS needs to follow when it needs to detect the deadlock. So allow the system to enter into deadlock, that means it allows the process to get executed. If suppose deadlock happens, it will identify it with an algorithm, detection algorithm, and it will recover it. And it is going to use a resource allocation graph, and also one more graph is called as wait for graph. So from the resource allocation graph, we are going to draw the wait for graph. So see in this diagram, the process P1 is allocated with resource R1 and resource R2 is allocated to P1. P1 is requesting R1. So you see the diagram, corresponding wait for graph diagram. P1 P1 is requesting P2 process. So see here, where is R1? P1 is requesting resource R1. So where is R1? R1 is with P2. That means P1 is waiting for the P2 process. That has been given in the corresponding wait for graph. P1 is waiting for P2. And similarly, P2 is requesting resource R3, and R3 is held by P5. That means P2 is waiting for resource P5. So see the diagram, you will have P2 is waiting for P5. Similarly, this wait for graph is drawn with the help of resource allocation graph, and it will see the wait for graph. OS will see the wait for graph. If that graph doesn't have any cycle or doesn't have any problem, then only the resources will be allocated, otherwise it will not be allocated. That means more than one process is waiting for one process. More than one process waiting for one process means definitely it will lead to a deadlock. So see the wait for graph, and it will allocate the resources. And if suppose the resources are having only single instance, it doesn't have more than multiple instances, it is having only single copy of it, then every time the algorithm needs to be invoked, because it is having only single instance, it is being allocated to a process, some process may be requesting the same resource instance. So that means it will periodically check with an algorithm whether a deadlock has been detected. If a deadlock has been detected, then it will do the remaining work. So that's why it is using the corresponding wait for graph for detecting the algorithm. And if it is using several instances, then it is going to use a detection algorithm. If the resources are only single instance, it will use a wait for graph for detecting the algorithm, and if the resources are multiple instances, then it will use the detection algorithm. So the detection algorithm, you have to check, we are having two variables, there is work and finish. Work equal to available resources will be stored in work. For every process I, 1 to n process, the allocation is 0. If allocation is not equal to 0, that means no allocation of resources has been made, then allocation not equal to 0. Then and also finish of I. I have already told you what is finish of I. If a process execution is completed for all the process, finish of I means if the process execution gets completed for that particular process Pi, then it is true, otherwise it will be false. So if allocation not equal to 0, then finish of I equal to false. That means nothing has been allocated, so definitely the process didn't have completed. That's why finish of I is false. Otherwise finish of I equal to true. So this will be checked for each and every process. Find an index I. You are going to find a process such that its finished state should be false and the request is less than work. What is work? Work is the availability. Availability of resources, take an example 50. and the requested resource is only 20. If the 20 is less than the available resources, the process can be allocated, otherwise it cannot be allocated. The same case, if it is asking for 80 and we are having only 50, we cannot allocate the resource to the process. If no, it will be checked for each and every process. If no such I exists, it is going to step 4. In the step 4, if finish of I is there equal to false till the end, then the system is in deadlock state. Then it can say a particular PI is deadlocked because its finish state is false, other process finish state is true. If one process finish state is false, that process is the deadlock process. And if suppose there is no false, the conditions are satisfied in the second step, then it will allocate the resources to the particular process and make the process to get completed, and the finish of I is true. Again, it will be continued for all the process. Only when all the process gets its finish of I becomes true, it will say the process has completed, otherwise it will say a particular process has been deadlocked. So this is the detection algorithm. Every time OS will use this algorithm after the process is allocated with the resource. So you have a safety algorithm, Banker's algorithm for checking whether the resource can be allocated to the process previously. In prior we are checking with the Banker's algorithm. But once the process has been allocated with the resources, we have to check it periodically whether it has come to the deadlock state. For that, you are going to use this detection algorithm for multiple instance and wait for graph for single instance. Right, and how will you recover from the deadlock? So once the deadlock has been identified, you have detected with the algorithm, how will you recover from the deadlock? So so many conditions are there. You have to abort all deadlock process. You have to remove all the deadlocked process. How can it possible? Whether a particular process is going to be a victim for every time? How? It is not possible, right? So we have to make some conditions for removing the deadlock from the system. Deadlock process from the system. Abort one process at a time until the cycle is eliminated. That means the OS will abort one process from the system, and again it will check the deadlock detection with the help of deadlock detection algorithm. If it finds any deadlock process over there, again it will remove that particular process, and again it will check with the deadlock detection algorithm until there is no deadlock, and all the deadlocked process has been removed. So we are going to abort only one process at a time and use the algorithm for the further checking. And how will you remove the process? In which case you will remove in what condition you will remove the processes? Priority of the process, depending on the priority of the process and how long the process has been computed, how much number of time it has taken to complete its execution, or how much time is needed for complete its execution, and how many resources it needs to complete its execution, how many it has been used, how many resources it has used, whether this set of process needs to be terminated, or it could be continued with some small changes, or we have to check whether the process is an interactive process or a batch process. What is the difference? Interactive processes, only one process at a time is being executed with the help of user interaction. So we cannot abort the process very easily when the user is interacting with the process. So we have to check that. If it is a batch process, all the process gets affected. If you are aborting one process from the batch process, all the process gets affected. So you have to check all these conditions, and if all the conditions are satisfying, then only the process can be removed from that particular system. So if the process is being removed, the remaining process can restart its execution and complete it, so there won't be any deadlock. So this is the work of the OS to check every time the process is executing with the CPU, when multiple processes is executing CPU. And how will you recover from the deadlock? Instead of removing resources or removing process, we can even recover from the deadlock with the help of three things. One is selecting a victim. So whichever process may lead to deadlock, if the OS thinks that a process if this process enters into that system, definitely it will lead to a deadlock, means you can make it as a victim. So that the cost will be minimized. Every time you don't need to apply the detection algorithm. Every time you invoke the detection algorithm, cost is more. The OS will take more time, so automatically the cost will be more. This is not for I am not talking about for a single operating system. If you are using in a company with what is that, the distributed system, and the server is having an operating system. Every time the distributed system is invoking the detection algorithm, the cost will be more for the company. So it needs to minimize the cost. That's why it will select one, it needs to select one process as a victim, and if that process doesn't need to be executed, if the OS thinks it is the main culprit for making the system into deadlock, it will not allow the process to execute, enter into that system. So you can select a victim, or you can roll back. So rollback is not all the times all the process is executing. Suppose 1 and 3 you have 4 process, 1 and 3 is executing now, 2 and 4 is already executed. So you can see that when 1 and 3 is getting executed, you are getting into a deadlock state, means you can roll back the state to where the 2 and 4 executed. You can roll back the state so that you can identify which process, whether 2 or 3 has made a deadlock. So you can identify the process, you can remove that, and you can restart the execution. So the rollback can be made. And starvation. So same process, if you are taking the same process as a victim, definitely it is a concept of starvation. So the same process is starving to complete its execution for a longer time. So it leads to a starvation. Instead, you use rollback. Rollback is the best method in order to avoid deadlock and also make the system to get completed clearly. I think you would have understood what is meant by deadlock and how it can be prevented, how it can be avoided. Deadlock is an important thing. Sometimes our system gets hanged. We don't know why it has hanged, because of deadlock only. So deadlock is an important part of operating system. So whenever an operating system programmer is programming, he needs to consider this deadlock algorithms, and then only the operating system can effectively work. Thank you.